In 2009, two satellites collided, 800 kilometers above Earth. The crash created thousands of debris fragments. They are still orbiting today. Each fragment is a potential trigger for the next collision. This chain reaction is called the Kessler syndrome. It threatens GPS, weather forecasting, and global communications. Satellite operators need to know, right now, what is about to come dangerously close. I built an AI agent that answers exactly that. Answering that question is not one calculation, it is an investigation. Fetch live orbital data, propagate the trajectories, find the close approaches, score their risk, and explain it all to a human. That is why I used a multi-agent system. A coordinator runs 3 specialized agents in sequence. A data agent screens and classifies conjunctions. An analysis agent measures how critical the object is in the debris network. And a briefing agent turns the numbers into a decision. The engines behind them are exposed through a custom MCP server. The risk classifier is the core of the system. I trained it on real conjunction data from the European Space Agency. 13,000 real events. But I made a deliberate choice. I used only the features my own pipeline can produce: distance, relative speed, and time to closest approach. I left out the covariance data that the challenge winners used. Less peak accuracy, yes, but the model actually runs on live data. And when 3 risk tiers proved unreliable, I reframed the problem as the binary decision operators really make: maneuver or not. Here it is, running. I give the agent a satellite. Cosmos 2251. I can use its name or its catalog number. The agent resolves it either way. Watch the 3 agents hand off. The data agent screens the live catalog and classifies each approach. The analysis agent computes the object's position in the risk network. And the briefing agent writes the verdict. It reports the actionable conjunctions with time to closest approach. It flags the object as a network hub. If it fragments, the cascade spreads, and it recommends a maneuver. Now, the same analysis, in 3 dimensions: the target, its risk neighbors, and a line igniting at each moment of closest approach. This is live orbital data, screened, scored, and visualized. So, how good is the model? It reaches a strong ranking score on held-out data from the Space Agency. On that test set, it catches 584 of 787 truly dangerous conjunctions. In a real system, you tune it toward recall, because missing a collision costs far more than a false alarm. And every number here is reproducible from the repository with a single script. This project applies 4 concepts from the course: a multi-agent system, a custom MCP server, secure credential handling, and a reproducible deployment. But what I am proudest of is not the plumbing, it is the judgment. Choosing real data over convenient labels, letting the domain define the problem, and being honest about the model's limits. The code and the full documentation are linked below. Thank you.